All right, so yesterday we talked about 2.4, and I pulled in here a little screenshot of the postulates that we talked about. This little screenshot is or the little picture would be in your book if you want to pull it in. It's kind of like summarizes the 1, 2, 3, 4, 5, 7 postulates that we talked about yesterday. Okay. Remember that while your warm-up and stuff might ask you for a number, what I really want you to know is the meat of the postulate. I want you to know what it says, not so much what the number is, because remember we said outside this book that number has no meaning to it, right? But that those postulates are true for every geometry course, okay? So those are things that are true no matter what, inside or outside this course. All right, so the directions for number 1 said use the diagram to write an example of postulate 7. Which was, if two lines intersect, then their intersection is exactly 1 point. So who can give me an example of something that they wrote based on this diagram that would showcase postulate 7? 100.
Line FJ intersects line EG at point F.
Perfect. So line, make this bigger. FJ intersects line, you said E, what'd you call it? EG at 1 point or at point F, okay? You could have called it FJ and EF, right? That's the same line. You could call it line M and line N. Those are also names for that line, okay? Anybody else give something different that they want to see if it's right? Or everybody had something like that? Okay, good. Number 2 says decide whether the statement, two planes can intersect in exactly 1 point R is true or false and give a reason. Chris?
False.
Why?
Because postulate 11 states that the intersection of two planes is a line.
Perfect. Intersection of two planes is a line. Questions on either of those? Okay, so it said building B is due west of building A. So wherever I put A, okay, then I have to put in relation to that B. So west is in which direction? Here's my little compass, right? North, south, east, west. Which west would be where? To the left of A. So it's anywhere over here. Then it says buildings A and B are on street 1. So I'm going to connect this and call this street 1. Then it said D is due north of building A. Due north would be straight up. And then it says A and D are on street 2. Put these on street 2. Then it says building C is southwest of building A. So southwest is going to be somewhere over here. Building C. God bless you. A and C are on street 3. And building E is due east of building B. So building E is due east of building B. So E is to the right of B. E could be here. E could be here. Okay? I don't know exactly where it is. I know it's due east, which means it's going to be to the right. And then the next thing says angle CAE formed by streets 1 and 3 is obtuse. So CAE, if I leave E on that side, does that look obtuse? No, which is what tells you that E has got to go on the other side. So E will stay here. Now I've got CAE here, which definitely looks obtuse. Now I've got my full drawing, right? So now the questions are, draw the diagram, which we just did. Where do streets 1 and 2 intersect? So 1 was my red and 2 is my purple. Those intersect at point A. Classify the angles formed by streets 1 and 2. 1 and 2 would meet at exactly 90 degrees because it said due north. So those would be right angles. Is E between buildings A and B? We just said no. In order for that obtuse angle to be formed, E had to be the outside of A and B. And then what street is building E on? And E would be on street 1. Make sense? Yeah, so you get a little bit of knowledge of north, south, east, west behind that. Okay. All right, any other questions from the homework? All right, so let's move. Okay, this one says use the diagram to determine if the statement is true or false. And this is like I said the other day. This is where Three-dimensional figures get a little tricky when you're looking at them on a two-dimensional page, right? So we've got a vertical plane, that M is a vertical plane, and N is slightly horizontal, okay, but at least it's like being tilted backwards. Remember that the dashed lines means that if that M was a solid plane, you would not see that part of plane M, or plane N, sorry. That's what the dashed lines mean. It would be, if those were solid figures, you wouldn't be able to see those. If they still exist, you just wouldn't be able to see it. All right, so number 3 says the intersection of planes M and N is points B, E, and H. True or false? I heard a lot of truths. Is that true? What did we just say the intersection of two planes are? A line. Are points E, B, and H, or E, B, and H a line? No, so be careful. Yes, E, B, and H lie on the line where those planes meet, okay? But they are not aligned, so this would be false. Okay. Number 4 says GH lies in plane M. So M is our vertical plane. Give it a little bit of color here. So M is this vertical plane. And it says GH. So GH would be segment GH, which is there. Does that lie on that vertical plane? Yes. Okay. The other way to look at it is, do points G and H lie on that plane? Because if the points lie on the plane, then what? Then the line that contains those points lie on that plane. All right, 5 says angle. So let me get rid of that color. Or not. I'll figure this out eventually. Here we go. Okay. So this was true. Angle ABE, so ABE is this angle here, and HED, which is HED, are vertical angles. False, okay? They don't even have the same center letter, right, which would be your first indication. They have to have the same vertex, right? They just have to point in opposite directions. What would be, give me a vertical angle to HED? BEF, you said? Yep, good. Come on. BEF would be a vertical angle. Does that make sense? Yes? Good? Okay. Flip to, catch that before. This should be section 5. Oh, sorry, Evan. So we're going to do a lot of properties today. Okay, so these, by way of, you could start to see some more flashcards in your future to help you remember this stuff, okay? We are stepping our way into proofs. And a proof is get from this to that and explain all the steps in between. Okay, so today we're going to talk about how you could give a reason for some of those steps, and then eventually you're going to try an algebraic proof on your own. So properties of equality. These are properties that carry over from algebra. Okay, so addition property of equality says that if A equals B and C equals D, then I can add the same thing to both sides of my equation and it would still remain true. So A plus C would equal B plus D. So if I'm adding the same thing or equal numbers to both sides, then my statement stays true. And subtraction is the same except you're subtracting. So if A equals B and C equals D, then A minus C equals B minus D. So if I'm subtracting the same thing or two equal things from either side of an equation, that would be the subtraction property. Multiplication is multiplying the same thing on either side of an equation. So if A equals B, then C times A equals C times B. And division, you're dividing the same thing on both sides of the equation. So if A equals B, then A divided by C would equal B divided by C. Why does it say C can't be 0? What happens when you divide something by 0? What?
It goes to 0.
What happens if you divide by 0? Because you can't divide by 0, that's why it says C cannot equal 0. Okay, you can divide by anything else. Anybody still copying it down? Okay, continue of the properties of equality. So then we get into substitution. Substitution property says if A equals B, then either A or B may be substituted for the other in any equation or inequality. So if 2A equaled 10, then 2B would equal 10. So we've substituted B in the place of A. The reflexive property is anything equals itself. Think about when you look at yourself and you're looking at your reflection, okay? You would be looking at yourself. Anything equals itself is reflexive. Symmetric says if A equals B, then B equals C. Then B equals A. So you're just switching the order on it. If you think about like an image or something that's symmetric, if you fold it in half, it overlaps, right? So if you took an if-then statement that was symmetric and you folded it along the then, the letters should match up. So the A would go where the A is, which is on the outside. The B would go where the B is, which is on the inside. Transitive says if A equals B and B equals C, then A equals C. So this is similar to the law of syllogism, right? Law of syllogism is almost like the transitive property for if-then statements, okay? So transitive says, so if I said Alejandra is the same age as Alexis and Alexis is the same age as Allison, what can we determine from that? Alejandra is the same age as Allison, okay? So think about transitive being the joining together of those two statements. And then distributive is a property you've been using for years, right? Anytime you've got parentheses and there's something on the outside, we distribute the number on the outside into both the properties, or however many terms are on the inside of the parentheses. That's distributive. Question on any of those? Okay, so transitive would be like if A equals 3 and 3 equals B, let's say, then A equals B. Or we're going to get into angles and stuff like that in a minute, where you'll see them applied to shapes or figures instead of just numbers. So it is a lot like your law of syllogism, where you're taking something that's repeated and you're taking it out and putting together the other two. It doesn't have to be in an if-then statement form. Okay, I could have said A equals 3, and I could have said B equals A. So now I know that B equals 3. So you're taking out whatever repeats and joining the other two together. So all of those, oh, sorry, Michael. Okay, so all of those properties apply to segments and angles. So a reflexive property obviously is true for numbers and variables, but it's also true for segments and angles. So if I said that, give me an example of a reflexive property using a segment, you could say something like DE equals DE. You're saying that a segment equals itself. And then angle D would equal angle D would be an example of a reflexive property applied to angles. Symmetric, remember that if I fold it along the then, it overlaps. So symmetric is the switch of the order. If DE equals FG, then FG equals DE. And with angles, if angle A equals angle B, then angle B equals angle A. And then transitive. So transitive is going to bring in a third object, either a third segment or a third angle. If AB equals CD and CD equals EF, then AB equals EF. So let's say I've got this line and it's not shown to scale because I'm not very good at spacing, but you can get the idea, all right? So if it said that AB equals CD, that would mean that these two are congruent, correct? And then I said CD equals EF, so those two are congruent. From that, you should be able to determine that AB equals EF. Right? So if I gave you the measurement, if I said that this was 5 and this was 5, I would know that this too was 5 because of the transitive property. Same is true for angles. So if angle A equals angle B and B equals angle C, then A equals angle C. We've taken out the part that repeats and joined the other two together. Questions so far? All right, so these are simple, like just if-then statements or equations, and it's asking you to justify them with a property from algebra or a property of congruence. So one of the properties we just talked about. So if I said if AB equals CD, then CD equals AB, what property is that? Lord, it's symmetric. Good. Okay, 2, if 3 parentheses x plus y equals 3x plus 3y, how do we get there? Distributive, good. If 2a plus b equals 34 and b equals 4a, then 2a plus 4a equals 24. What'd you do? So transitive, you're going to see 2 if-then statements if it helps. This, what changed from here to here? No. Claudia, good. Yeah. You took out the b and replaced it with the 4a, which is substitution. And the last one, if x over 3 equals 12, then x equals 36. How do we get from the if to the then? Multiplication. Good. Okay, so remember I said we're going to baby step our way into these algebraic proofs. So this is a step-by-step process of how someone would solve this equation. And your job is to justify each step. So the question with justifying is, how did I get, God bless you, how did I get from the statement above to the statement I'm on? Okay? The initial statement, this problem, is not something that just appears out of the blue. This is given to you. So that's how we justify the very first statement of a problem. That equation would have been given to somebody to solve, right? So we would write given. So let's say that this is step 1 and this is reason 1. Now how did we get from step 1 to step 2?
Multiply by 3.
Good. So we multiplied, which is the multiplication property. And technically it's multiplication, property of equality. Then how'd you get from step 2 to step 3, Chris? Distributive. How'd we get from step 3 to step 4? Good, Emma. Addition. And how do we get from step 4 to step 5? Good. I'm actually going to add to this. So if you want to scroll down to the next page so we can add on a problem, we're going to go to the next step because your homework's going to ask you to do it, which is solve the problem on your own and justify your statements. Okay? So this time they actually gave you the step-by-step of the solving. I'm going to give you one. All right, so what would be the reason you write next to the first thing? Given, because I gave that problem to you, right? Okay, 2. What could be your next step? Because there's more than one way to solve this. Nick, you added 3 to the other side, right? So if I added 3 to the other side, what's my next line look like?
1/2 x equals 36.
And that's the addition property. Okay, then what'd you do? Nick, what'd you do?
Oh, I multiplied
Multiplied by? 2? So you got x equals 26. Super easy, right? Don't overthink it, okay? So you could have, from step 1 to 2, multiplied everything by 2 and gotten rid of a fraction. That could have been something. Anybody do that? Okay? So then your next line would have been x minus 6 equals 20, right? And your reason would be multiplication instead of addition. And then the next line, you would have added the 6, okay? And you would have gotten x equals 26. It's still totally right. So the order doesn't necessarily have to be in a certain way. But you just want to make sure that you're justifying the steps to get from the one before it to the one you're on. Questions? Okay, so I'm going to do 28 says, or the directions say in exercise 28 and 29, show that the perimeter of triangle ABC is equal to the perimeter of triangle ADC. So before you even get to like showing that, does that make sense? Does it make sense that perimeter ABC is equal to the perimeter of ADC? Yeah. So if it's hard to see, you can always give it a value and see if it makes sense. So like if I said that side DC was 3, then what else would you know is 3? CB is also 3. Okay? If I said AD was 4, what else is 4? AB is also 4. So then what's the leftover side for each of those triangles? AC. And if I pulled those triangles apart, would AC be the same as AC? Yeah. What do you think that's called? What property is that? If I pull those apart and AC is in both, AC equals AC? Reflective. Okay? So that property tells me that no matter what, if I were to pull, say if I pull those apart, now they're two triangles, AC is still always going to equal itself. Does that make sense? So let's say that this was 2, no matter what, if I pulled them apart so that it was 2 different triangles, I'd still have 3, 2, 4, and I'd still have 3, 2, 4. You with me? So now the question is, show that that's equal. How do you do that? And there's no exact science to this, but how would I show the perimeter for triangle ACD if there was no numbers? How do you figure out perimeter? Add up all the sides, right? So if I said triangle ACD would equal AC plus CD plus AD. And triangle ACB would equal AB plus BC plus AC. And then in your words, because again, this doesn't have to be exact, you could say something like the AB equals, so AB equaled AD. These two are equal. You could show that BC equals CD. These two are equal. And then we know that these two are equal because they're the same. So you literally could have written that out word for word. You could have shown it using numeric values to give yourself examples, okay? Like I said, we're kind of baby stepping our way into what's called a proof, where we would have to justify that step by step. For right now, you're in an explain process. So show that the perimeter would be equal. So you're going to have to, I'm going to publish it right now, but you're going to have to do the same thing to 29, okay? Just so you can get an idea of what that might look like.